Continue. I'm gonna make a comment about last time's theorem. I made some mistakes. So let's recall this Erdős guideline condition. So eventually the proof is much more complicated than I thought. So, but I want to make a summary so you know what is going on. So this theorem says the following. Let me repeat. So you have this degree sequence. So we have this theorem. So we write down a degree sequence. D1, D2 until Dn. So this is this degree sequence is not necessarily decreasing at this point. Okay, so before stating the theorem, and then we sometimes make it decreasing. So what I'm trying to say is that we can consider this as to be a graphic if we can list V1 until Vn such that dk equals the degree of vk for all k. Okay, so this definition is made for all possible. Let's just definition is made for all possible sequences. But for the convenience of the proof, sometimes we ask it to be decreasing. This is important later. So, for example, we have this key proposition saying that if D bar D1, D2 is indeed decreasing, and then we can obtain D prime bar, which is which is D2 minus 1, D3 minus 1 until D1 plus 1 minus 1, and then we have D1 plus 2 and so on, and the Dn. Okay, so we get this by the algorithm of HH. Let's put HH algorithm. So by the HH algorithm. But the problem is this time now, this if we start with D bar, but this D prime bar is not necessarily decreasing anymore. Okay, and the proposition says that D bar is graphic if and only if D prime bar is graphic. Okay, so there is a problem. There is a mistake I made last time. The thing is, this algorithm, you have to start with a decreasing sequence, but the result is not necessarily decreasing. But still, in this case, D bar is graphic if and only if D prime bar is graphic. Okay, so we need this proposition to prove the following theorem by Erdős and the guideline. So Erdős and the guideline says the following: take a sequence which is decreasing. So D bar equals D1, D2, and so on, Dn, which is decreasing. then D bar is graphic. So if and only if. So first of all, the sum of dk k from 1 to n is an even number. And 2, for all k, you have this inequality. The sum from j from 1 to k dj, it is smaller or equal than k times k minus 1 plus the sum j from k plus 1 to n, the mean number of k and the dj. Okay, so we have this star. So at the statement of this theorem, addition and guideline, we have to ask this sequence to be decreasing because this point 2, because there is a problem of order. So this is a true for this decreasing order. Okay, so you have this. So the proof of this theorem is more complicated than I thought. So the proof of the theorem is that we want to so the first step is proposition. The key proposition is true. So okay. So how to prove this? So okay. So the theorem, we use induction kind of induction scheme. So the theorem is true for D bar. We want to show that it is equivalent with the theorem is true for what? Not for D prime bar. The problem is that D prime bar is not necessarily a decreasing sequence. Okay? You see what's going on? So we have to prove the following. We have to prove that this is true for D bar if and only if it is true for D prime bar, where D prime bar is obtained by firstly performing HH algorithm, and then reordering. So there is a step I missed. You have to do this. So essentially you have to prove this equivalence. So to prove that so the proof of this equivalence is by the proposition. So you use the proposition because to prove that this is graphic, okay, if and only if this D prime bar is graphic, and if you reorder the sequence, it's just the same as you reorder the vertices, so it doesn't affect if this sequence is graphic or not. But in order to make sense to this theorem, you have to make it to be decreasing, okay? Because you want to verify this star. So after the HH algorithm, you have to reorder it to obtain a decreasing sequence, which we call D prime bar, and it's equivalent to show that for D prime bar, the two conditions hold. Okay. So this is only one induction step, because D prime bar is simpler, is a kind of smaller. The integers are smaller, and then you keep reducing until you arrive at the zero sequence. If you eventually have a zero sequence, clearly zero sequence is the degree sequence of empty graph, and it satisfies, for example, star. So combine everything, you arrive at the theorem. So it's more complicated. So we are only able to prove a key proposition. So as for how to apply this proposition to prove this theorem is more complicated as I thought. That okay, okay. So, okay, any questions? Okay, so we just I made a mistake. So this so the full proof is a paper is more complicated than I thought. So today we we get into a kind of a topic. So the first lecture we gave us some general introductions, and the second lecture we talk about degrees of vertices. These are all simple properties. Now we today we give we talk about a topic which was generally regarded as the starting point of the whole area of graph theory. So it is a topic of Euler truths. So Euler, everyone knows, is a famous mathematician. I think he's from Switzerland. I'm not sure, but he also worked in Russia, and he has a very he has started a lot of branches in mathematics and did a lot of things. So historically, there is a city in I think in Germany, so called Königsberg. So the city has several bridges connecting. It's like there is a river passing through the city, and there are several bridges. So local people try to do the following. They try to start from one position in the city, and they try to walk through all the 7 bridges. There are 7 bridges. So in the city of, there are 7 bridges. If you search, you can find this picture of the city. And people try to walk through all 7 bridges. And they try to do it such that they start from some place and they also finish at that place. Okay? And no one can do it. So eventually okay, I think it's a fun entertainment for local people, but nobody tries to abstract this into mathematical problems until Euler realize you can translate this into a graph theory problem and solve it. Okay, so after the translation, I forget about this story. So after the translation, the map of Königsberg is something like this. So you have a graph. This is a vertex, and they have, for example, let's call this B, C, D. Okay, so there is an edge here, there is an edge here, and there are 2 edges. So this graph is not a simple graph. Mostly in this course we will talk about simple graphs, but this one is not. So maybe we call this edge E1 and this edge E2 and maybe this edge E3. So there is another edge which maybe F whatsoever. We only talk about these 3 edges. So maybe this is E4. Okay. So there are 2 edges connecting B and C. So what local people are trying to do is that they want to start from one point, and they want to cross all 7 edges and come back to this point. And they want to do this in a way that you do not walk through one edge twice. Okay, so I think if you ever do Olympiad problems, this kind of thing has a lot of variations in Olympiad problems. Have you seen this kind of thing? Yeah, so yeah, right, great. So there's a so Euler observes that this really depending on the this really depends on the degree of every vertex, and more specifically, it depends on the parity of the degree. So the degree, you have odd number of edges or even number of edges. So this is a very interesting discovery. If you look at now, it's not particularly difficult, but it involves a lot of definitions. So when you introduce a lot of definitions, so probably you feel a little overwhelming, but you don't need really to remember them. So each time, so it's really important each time when you are talking mathematics and discussing math problems with some person, some other people, everyone should be sure about definitions. You have to fix a set of definitions and then discuss problems. Otherwise, you don't know what's going on. But there are a lot of definitions because there are a lot of different situations. For example, we talk about a walk. So the story starts by walking through a town. So a walk becomes a definition in mathematics. A walk is a sequence of vertices, edges, and alternatively. Or maybe I say alternative symbols. Okay, so for example, probably we have V0, this is the vertex, and E1, V1, E2, V2, something like this. In this case, we have A, so this is an example. So in this case, maybe we'll talk about A, E1, B, E1. We can come back, okay? So that's a point. A walk can repeat itself. And B, E1A, and maybe E2C, and E3B, whatever, okay? Okay, so the general definition, you don't have any restrictions. You can come back and forth. Well, a trial is a walk. First of all, it's a walk with no edge repeated. Okay, so for example, here you get E1 again, so it's not a trial. So a trial is something that if you go through E1, you will never do it again. Okay, so a pass is a trial that no vertex is repeated. Okay, where no vertex is repeated. So here we arrive at this definition of a pass. We did it again. So before we did it before. So in the first lecture, we already gave a definition of a pass. So the two definitions are the same, are equivalent. So here it's just it becomes more and more specific. A walk you can do anything, and a trial you cannot repeat edge, and a pass you cannot repeat vertex. So it's something like you have V1, V2, for example. Let's start with V0. Okay, V0, V1, V2, and so on. So you arrive at Vk plus minus 1. Okay, so this is a pass. And a cycle is not, by this definition, is not a pass. So maybe let's say it's a trial where only the starting vertex and the ending vertex are repeated. So let's say Okay, only this. So how to say that? So that's a trial with where starting vertex is the same with the ending vertex, and except this, no other vertices repeated. Okay, so everyone knows what's going on, but you have to make this precise. So you have V0, maybe V1, and so on. You get Vk minus 1, and you come back. It equals Vk. Okay, something like this. So this is a cycle. Okay, so we have even more definitions. So a closed walk, it's like a cycle. A closed walk, it's just it's a walk with let's write it with in a simple way. So with V0 equals Vk. So you start from V0 and you arrive, come back at V0. So during the whole walk, you don't have restrictions with repeated edges or vertices. Okay, and a closed while is something similar. So let's first of all, V0 equals Vk, and no edges repeated, no edge repeated. Okay, so it's called a closed file. So so after all this, what this problem asks for? So really, it asks for the existence of a closed trial. You are allowed to repeat some vertices, but you have to start from a point A, for example, and arrive at A eventually, and don't repeat edges. So you can repeat vertices and you cannot repeat edges. And you start from some point and you end there. Okay, in this case, we call it Euler trial. Okay, final definition. So in a graph G equals VE, we call Euler term. Okay, so which is a closed trial. Closed trial. Well, which covers all edges. Okay, do you agree? So remember, the problem asks you to go all bridges. So a closed trial, maybe, for example, in this picture there, I can draw A, B, and C and come back. This is a closed trial, but it does not cover all edges. What's going on is you have to cover all edges, and then you call this a Euler trial. And similarly, an Euler trial. Be careful, here is not a closed trial, okay? A Euler trial. So you are allowed to start and end in two different vertices. Is satisfies that is such that it starts at some V0 and ends at some Vk, for example. Okay, and it covers all edges. It has to be a trial so that no edge is repeated. Okay, this is contained in the definition of a trial. Okay. Questions?
What's the difference between a closed walk and a cycle?
Okay, so a cycle, you cannot repeat any, you cannot repeat a cycle is something like this. Okay, so for example, you have V1, V2, V3, V4. This is a cycle. It's okay. So now it's possible you get V1, something like this. It's not very good. So this is V1 again. So V2, and then maybe we decide to put V4, V3, maybe V2 again, and come back to V1. Okay, this can be a walk. Is it clear? So a walk, you can repeat edges and as well as vertices. A cycle, you cannot repeat anything. You cannot repeat. I mean, this is the same edge. So okay, so a walk can be this is E1. I draw too many things, so I make this simpler. I think three vertices are enough. So a cycle, you get, for example, V1, V2, and V3. Okay, so a walk, you can be something like this. So this is the picture. You have V1, V2, V3, and you have, for example, E1, E2, E3. So by definition, a closed walk, it could be a V1, E1, V2, and come back E1, V1, E3, V3, and E2, V2, and E1, V1. Okay. Do I answer your question?
Yeah, thank you.
Okay, so it's just you are allowed to come back, so you can walk back and forth and so on. So cycle is a thing, is object. So walk is kind of you can imagine someone is actually walking. But this kind of definitions, like I said, unless you are trying to do some very specific work, trying to solve some problems, and then you realize you have to talk about different things. So otherwise, you don't need to remember them for now. Okay. So okay. Now we eventually have this. After all this, we have this question. So in a graph, for example, that ball graph, in a connected graph. So if it's not connected, it's a little strange. Okay. So you cannot go from one point to the other, to another. So we assume we have a connected graph. So in a connected graph, G is there and Euler tour or no? Oh, another question, is there an Euler trial? So these are two questions. They are related. Okay, can you find the Euler tour? Can you find the Euler trial? Remember, Euler trial is something like you go from V0 and you arrive at VK and something like this. So you can, okay, it's better to do something like this, probably like this and this. Okay, this is a Euler trial. So I mean, you can, for example, this point, this vertex V1, you can visit twice, but you cannot visit an edge twice. So if there is a direction for convenience, maybe I do not draw. Okay, I don't want to confuse you with directed graph. It's not directed graph. For example, we move from V0 to V1 and this edge is used. We cannot use it again. But we can do this, and come back to use V1 again, as long as we do not use one edge twice. So this is a Euler trial. And Euler tour, you have to something. So if you have the same picture, it's not good enough. you have to do this. So probably this V1, V2. We do this, and I don't know, V3, V4, V5, V6, V7, V8. So this is a unilateral. And after you draw this unilateral, you don't have any other edges left. The same for Euler trial. You cover all the edges, but you are allowed to start and end in different vertices. And here you also cover every edge, but you start from V1 and you have to finish at V1. So this is the question, the theorem, the key theorem of today. So it turns out to be an easy theorem, not so difficult. So a connected graph. G admits an unilateral if and only if every vertex is even. So what is even vertex? The degree is even, okay? So, or maybe I don't use a notation. So let's say every vertex has even degree. Okay, so 2. Again, G admits an Euler trial if and only if exactly 2 vertices have odd degree. Okay. The proof, I will do it, is not particularly difficult, but it's really something you should learn. So you have try to extract some information and eventually prove a theorem. Okay, so like this situation, this degree of V0 is 1, and the degree of VK is 1, and this has degree 2, and this has degree 4, 2, 2, 2. Okay, so V0 and VK has degree odd, and all other vertices have degree even. And in this case, all vertices have degree even. Okay. But we have to prove this. So first of all, I want to show that 1 and 2 are equivalent. Okay, this is a clever observation. So why is that? Because suppose for example G, I will not write all details, but you will understand. So suppose that so G is say it admits so let's say let's say G has all vertex has all vertices with even degree. Okay, so the situation in 1. Okay, so right, there is a problem. Right. So I think it's easier to say that the G has exactly 2 odd vertices. Two odd vertices. Say V0 and let's say V and V prime. Okay, so in situation 2, so let's say 2 is equivalent to 1. It's easier. Okay, and So what we want to do, we want add a new edge, just VV prime to G. Okay? And then we call this new graph, let's say, to obtain a new graph, G prime. So what happens for G prime? So note that G prime, in G prime, every vertex has even degree. Do you agree? Because in G, V and V prime have odd degrees. But by adding this edge, both degree of V and V prime increase by 1. Okay? So we kind of using this technique to change the problem back and forth. Okay. So now G prime, if for example one of the statements is correct, if G prime in G prime, every vertex has degree even and it has a Euler tour, then you delete that edge and you observe that original graph has a Euler trial. Okay. But the other direction actually is a little more tricky to prove. For example, you start with a graph with all degrees even. Why I start there and go stuck? Because it looks that it's possible if you delete one edge, the graph may becomes disconnected. But this will not happen, but you have to prove it. So it's not a complete proof, but you can think about this. Okay. So on the other hand, let's say, on the other hand, if, for example, H, if in H, every vertex has a even degree, okay, we claim first. So I think it's enough to find that there exists one edge, E, such that H minus E is still connected. You have to prove this claim first. Okay, it's not very difficult, okay, but you have to prove this. And then you can do, you can delete it, and then you realize that, for example, E is V prime, then H minus E has exactly 2 vertices with odd degree. Okay, degrees. And then, but you have to make sure this is also connected. Then you can use the second point to find the Euler trial for H prime. Okay, so this graph is called H prime. So there is a Euler trial for H prime. And you add back the edge E, you find the Euler trial for H. Okay. Okay, great. So so let's so after this we see that the two statements are equivalent, and then we start to prove. So let's prove only 2 then. So we prove 2 then. We only prove point 2, the statement for Euler trial. Okay. Okay. So to prove two, we have two directions. The first direction is obvious, because if you have a Euler trial, something like this, and start, you don't know what happened during the whole process, and you end at another place, like I explained. You have this guy and this guy, but so V0 is not equal to Vk. Okay, the degree of V0 and the degree of Vk have to be odd, not necessarily 1. Okay, so for example, this is the first time you arrive at Vk, but maybe you decide to go away. Okay, and then you arrive at Vk again, and at the point Vk. So maybe it has a degree 3, but you know that both Vk and the V0 are odd, and all other vertices have degree even. Is it clear why, for example, you have V here, it has a degree even? I think it's clear because you're following the trial. You're following the trial. Every time you have an edge through which you arrive at V, you must have another edge such that you are leaving V, because eventually you are not at V. Okay, you start from V0 and you arrive at Vk. Only these 2 points, vertices, are kind of special. Okay. So this direction is actually obvious. What's difficult is the other direction. So suppose, let's say V0 and V1 are the only odd vertices of G. And we are trying to find a trial which visit everything, which will pass through all the edges. Okay. So the idea is the following. So we try to find a trial as long as possible. And if you can still extend the trial, you do it, because there are only finite things to do. In total, you can do only finite things. Every time, if you find the edge, you cannot use it anymore. The total number of edges are finite. So eventually you have to stop. And we argue that you have to stop at V1. Okay, this is the first step. It's not the complete proof. So let's say we start with V0 and try to construct a trial as long as possible. Okay, so no edge. So it's a trial and no edge can be reused to have this condition. Okay, so it has to be a trial. Well, it cannot be a walk. It's a trial, general walk. So this is contained in the definition of trial. Okay, but vertices can be repeated. Okay, there's no problem. So every time, so let's analyze the situation. Every time when we arrive at a vertex, so if this vertex is not V1, we started from V0. If not V1, then we know that, for example, V not equal. If V is not V1, then we know that the degree of V is even. So we have used one edge to arrive at V. So it means that there are at least one other edges we haven't used. Is it clear? So there is at least some other edge that has not been used. Okay, so we can use it now to extend the trial. Okay, this is, I think, a kind of important step. Is it clear? Unless we arrive at the point V1, because V1 has all the degree, so we are not saying anything. We are so far we are just saying that if we arrive at some vertex V, which is not V1, because the degree of V is even, we can continue. In particular, our trial cannot be the longest, because we can still extend it. We can still extend it. Okay, do you agree? And now we conclude that we can find a trial from V0 to V1. Because every time if you are not V1, if V is not V1, we can continue. But we have to stop at some point. So the only way to stop this process is to arrive at V1. Okay, this is kind of the first step. We are not finished because we are not guaranteed that we already passed through all edges. So let's denote this trial to be P. For example, P. P is right trial. Okay, T for this trial. Now we look at the graph G minus T. So we delete this trial from the original graph G. This time, this graph has all vertices even degree. Okay, so imagine we have something like this. Okay, so this is V0 and this is V1, this is V2, and this is V3, and this is V4, for example. And our first step, we find a trial V0, V1, V2, for example. Okay, so it's a fine. So you start from V0 and you end at V2, but it's not the whole graph. So this is our T. And the G minus T is what? Is this triangle. V1, V3, and V4. Okay. It has this particular property that all vertices have even degree. Because in the beginning we have two odd degree vertices. But this trial use V0 and V2, for example, exactly even odd degrees. So by deleting them, the remaining graph have all vertices even. Okay, but at this point, we have to apply a kind of induction. So this induction meaning that, okay, so this graph must admit an Euler tour. Okay, and you can add this Euler tour together with our trial to become an Euler trial. So here we have to apply induction step to find, and for example, Euler tour. Say C. For I don't know how to for example W0, W1 until W0. Okay, WK, W0. So this is a Euler tour. Okay. Actually, okay, there is another issue. There is a possibility that it's not connected. Okay, so let's say find the Euler tours for each connected components of G minus T. Okay, finally, we combine T with all these Euler tours to obtain an Euler trial. Okay, so this process only gives you a trial. It satisfies, which we call T. It satisfies the start. It satisfies the following. So it starts with V0 and it ends to V1. This is okay, but it's not necessarily a Euler trial because maybe it does not cover several edges. By deleting it, we obtain an even graph. Sometimes we call this kind of graph even graph. All degrees even. But for even graph, we invoke point 1. So it's a little strange, but you have to think clearly. This is not a cyclic proof, okay? So there is no cyclical reasoning here because you start with the induction with the edge number of the graphs, okay? And then at this point, you want to apply point 1. Suppose point 1 is proved for all smaller edge numbers. So you apply this to find the Euler tour for each connected component of G minus T. Okay, and then you combine. So the combine means what? For example, you have this V T is V1, V0, V1, V2, and maybe the Euler tour in this case is V1, V3, V4, and maybe here. So let's delete this guy. Okay. Only this. So this is the Euler tour. V1, V3, V4. So then together we get a Euler trial, which starts, for example, V0, and when you arrive at V1, okay, so actually something like this, V1, V3, V4, and back to V1. So we do V1, V3, V4, and back to V1. Okay, so we kind of insert this into V1 and then V2. So this is a Euler curve. Trial. Okay, so this is an ordinary trial. It's just a trial. So we get a trial and we observe every connected component, and we use this Euler tour start from V1 and come back to V1 and insert it here to get it Euler trial. Okay, so we have something like a 10 minutes break. We come back and 4 o'clock and 10 minutes. My screen. So I have a comment. So actually proving a Euler trial is a little more complicated. So if you only consider one, so a graph G, connected graph G, is so has a Euler for if and only if G is what we call an even graph. Every vertex has an even degree. Okay. So if you try to prove this statement, it's kind of easier. Okay. So you just you start from vertex v1 and you do this argument, some vertex v, and you do this argument similar to what we did earlier. So you just try to find a trial, a trial. Do not repeat edges, but you are allowed to repeat vertices. But every time you arrive at some point v prime, you have to leave. You are able to leave it, right? Because when you arrive at it, you use one of its degree, but it has degree even. Every vertex has degree even, so you have to you can go away, and eventually. So because this happens for every vertex, if you arrive at W, you can go away. But eventually, you argue that you have to arrive at V itself. Then you get a tour. But this tour may not exhaust all the edges. So for example, you got this tour you call T, a tour maybe you call C, and then G minus C, it might not be connected. Okay. So but it's an uneven graph, and then you use induction to find all tours, to cover every connected component by a tour, and you can obtain a tour which is a union of everything. Okay. So if you think of this, a tour does not really has a starting point. So you start with V, and you also can think of this as starting with V prime. So all the tours can actually be unioned together. So you can define one tour. So the difficulty really is how do you write this? Okay. So I will leave this statement as an exercise for you to practice. Okay. So I think it's kind of easier if you forget about trials. So it's easier. I choose to explain the trials, but I think it's easier to prove a tour. Okay. So I think at this point is a good it's a convenient time to talk about a little bit more about digraphs. So about digraphs, we have D, which is V, and a set of arcs. So it's like edges, but arcs has a direction. For example, you have something like this. You have V1, V2, V3, and maybe V3 to V4, and V4 to V1, and you decide to have also V1 to V4. So every edge has a direction. Okay, so in this situation, for every vertex V, we have 2 degrees. The alt degree, which is the number of edges, arcs, which come out of V. Okay, and the V minus D minus V is the number of arcs which come into V. Okay, so this is an outer degree. and this is the in degree. We have two notions to make a difference. For example, this guy has out degree V1, has out degree 2, and in degree 1. Okay, something like this. So we can very similarly define many things. For example, directed. For example, I do not write everything, but we can define something like a directed walk is something like V1, for example, A1, V0, A1, V1, A2, V2, and then A3, whatever, V3. Okay, so you can repeat, but and so on. But where you have a requirement that A1 equals V0, V1. So A1, if you are working with a multi-graph, you don't want to write equal. So it's just let's say where A, for example, A2 here is an arc from V1 to V2, because it's possible from V1 to V2 we have several arcs. So this is a lot, okay? But at least A2 is here. A2 is at least one of them. So this is a kind of a directed walk. Okay, you can define everything, trial and so on, and you can repeat also for a walk. Okay, but trial maybe you cannot repeat arcs and okay. So for directed graph, things becomes a little complicated. So in order to formulate something similar to this theorem of Euler before, we need another definition, kind of special for a directed graph. So we say this D equals V and A to be strongly connected. So the thing is in the directed graph, maybe we have some V and we follow the arrows, follow the arcs to arrive at W. But we don't have a sequence of arcs to connect W back to V. You see, for example, this simple directed graph, we can, if we are required to follow all the arcs, we can go from V and arrive at W, but we cannot start from W and arrive at V. We say a graph is strongly connected. So and the problem is that this digraph is connected. No problem. Okay. So we cannot say it's not connected. It's connected, but it's not connected enough. Okay. So we kind of want to define something called strongly connected. If for any choice V, W, there is, so let's say V1, V2, there is a walk, a directed walk from V1 to V2. So in this case, we call this digraph is strongly connected. So if you think of this, if we want to do something like Euler's theorem to find an Euler tour, this strongly connectivity should be necessary. For example, you cannot, for example, have something like this. This is V, this is W. For this directed graph, you are not able to find the Euler tour, because when you arrive at W, you will never come back. You're nowhere to go. Okay, it's out degree 0. You cannot go away from W. So the next theorem should be expected. The proof is similar to what we have done, but you have to understand these extra property. So suppose you have to suppose this. Suppose D is strongly connected. So this condition is you have to assume. Then the following is true. Then D admits an Euler if and only if what? It's a little different. The condition is a little different. For every vertex, V, the out degree of V equals the in degree of V. Okay? So it's a little different, but it also makes sense. So you ask something stronger than before. Every time you arrive at V, you kind of used 1 degree from here. You used one of the in degrees. And then at this point, you must allow yourself to leave the point, to go away from this point. So you have to choose 1 degree from the odd degree also. So this condition guarantees this. So for every vertex, the number of ways to go away from the point, the vertex, is equal to the number of ways you arrive at that vertex. Okay, do you think this formulation makes sense? And it's and you can and also you can kind of imagine how to modify the proof of the theorem to obtain a proof of this theorem. So I leave this as an exercise for you too. So we have 2 exercises, basically the same thing, but you have to manipulate with all these definitions. Okay, I think this directed one is a little more complicated. I put it as exercise 5, and you have an induction and so on. So you have to argue a little bit. You have to say that that kind of arguments. Once you arrive at some point, you must leave. Okay, something like this. You try to think about this, how to make a proper arguments in to make this. Okay, great. So still these okay, so okay, so to make your life a little easier, so let me prove one theorem related to this, not exactly the same. You will not use the result of this theorem, but I want to show you how to make arguments. So we give another definition. We say in a directed graph, D VA, we say Y is reachable from X if there exists a directed walk from X to Y. Okay. So in this sense, so this is another definition. In this sense, this digraph is strongly connected if every from every V1, every V2 is reachable. Okay, so it's just another definition. Okay, so if for every X, Y is always reachable from X for every XY, then we say the graph is strongly connected. So here there is a theorem. Really, it's about different thing, but the argument is similar. So X, Y are two vertices. So Y is reachable from X if and only if the following happens. For any X vertex subset, for any vertex subset which contains X and not contain Y, so let's say the outer boundary of X is not empty. So here is another notation. What is the outer boundary? So here, the outer boundary of a subset X is just the set of arcs such that A equals VW. V belongs to X and W does not belong to X. So it's kind of an outer boundary. It's something like this is X in a very non-rigorous picture. So you have an arc like this. Okay, so this W, this is V. W is not in X and V is in X. So it's kind of for example, if you have one vertex, you probably write the outer boundary of V. So one vertex V. So V probably have several out, several in. The outer boundary is these arcs. For example, this is A1 and A2. So this is V. So the outer boundary of V is just A1 and A2, right? But if you have several vertex and it's a set, so probably you have some inside arcs and maybe something like this, and you count all the outer arcs, which start from vertex inside X and at some point some vertex outside X. So I think this definition is clear. Okay, so you always, so for all X which contains X but does not contain Y, this X you always can find a way to get out of it. Okay, in words. So if you describe this condition in words. Okay, so the proof. We don't need this. So this is a equivalent. This is a characterizing condition for vertex Y to be reachable from X. Okay, so let's start with this direction. Let's say Y is reachable from X, so you can actually find a walk. You have a directed walk. Maybe you call W. Let W be a directed walk from X to Y. Y is reachable from X, so you'll find that there exists such a thing. There is a directed walk from X to Y. So we want to prove this condition, okay? And then take, because we want to prove this, take X contain X. It's a vertex subset, and X does not contain Y. And we want to prove that the outer boundary of X is not empty. In order to do this, you just find one arc is enough. Okay, you just find one arc to exactly leave the set X. And this arc is kind of is there. Okay, you just how to find this arc. So because you see, because this walk it eventually will arrive at some point y not in x. Let's say, note that the walk w eventually arrives at a vertex y, which is not in x. Okay, because of this. So we actually we if we follow the walk w, there is a moment or there is a vertex, is the last vertex. So how to say this? There is a time, there is a moment at which we stay in x. Okay, let's say where there is a last moment at which we stay at x. Or say that, in other words, so if you follow w, there is a w. So it's one of the vertices in w, and the w belong to x, and all vertices after w do not belong to x. Okay, so in particular, if we follow w, so if w prime is the arc following it, we know that w prime does not belong to x. So we find this edge arc. So this a equals w prime, it belongs to the boundary of x. So in particular, this is not empty. Okay, is it clear? So I don't know if you have learned some advanced analysis or linear algebra. So the thing is, sometimes at this phase in your mathematical study, you realize something is very obvious, but you have to write very precise words. So it comes off if you never do this kind of argument, it could be very requiring for you. But if you already seen it in, for example, linear algebra, you know what I'm talking about. So I think it's easier to describe and wave hands to you to explain the situation. But when you are actually write down the arguments, it's another story. Okay, so you follow this walk, and there is a one point, one vertex. After it must leave the set x. This moment exists because eventually, because at point y, you are outside of the set x. Okay, so this is kind of this direction, and the other direction, we assume that all x with this property has all degree non-empty. Then we try to prove that y is reachable from x. So suppose for contradiction, that y is not reachable from X. You will see how the boundary thing comes out. Okay, so then what do we want to do? We define X to be all the vertices that are reachable from X. Okay, to be the set of all the vertices that are reachable from X. Okay, because our assumption, therefore, Y is not in X. So I think this is something we want to obtain. Okay, because we assume that Y is not reachable, and we take all the points of vertices that are reachable, and we call it X. So therefore, Y is not in X. X is X. This is obvious because X you don't need to move. You reach X by a zero walk. You stay there. So this X, we want to show that this X actually has empty out boundary. Okay. So now we got a contradiction because all sets with this property, it should have a non-empty out boundary. So we will prove that the out boundary of X is empty. I think it's pretty clear, right? Because if not, suppose we have something arc A, which is W prime belonging to this out boundary. So for example, this is our X, and you have this arc, which is a W prime. Okay, and it's in the out boundary. Then what's going on? Here is my X. So remember, so this means what? It's in the, by definition, W prime cannot be in X. So out boundary means that this arc must move from X to outside X. So W prime is not in X. Okay, so we will find a contradiction with this. So now, remember, W is reachable from X. W is reachable from X. So meaning that there is some walk, which we call W, which is X, etc., until W. You go from X to W. And then we define W prime, which is just you put W here. You go from X to W, and then you add this arc, W arc, W prime. Okay, so we just write this arc W prime, and you put W prime at the end. So this is the form of a walk. So this W prime then what does it mean? It means that W prime is reachable from X, a contradiction. Okay, so W prime is not in X. Okay. Because by definition, big X is all the vertices that are reachable from X. So we got a contradiction. Okay. So this is a very interesting theorem, I think. All right. So what else? Okay, so I think I want to explain one more thing. So if you read my notes, the order of the exposition is changed. I decided to talk about the directed graph first, but in fact, recall this theorem of Euler saying that a connected graph. Let's come back to graph, saying that a connected graph is admits Euler-Tour if and only if it's a even graph, right? So there is an interesting corollary. I think I should mention it. So, and the final theorem for today. Okay, let's come back to a regular graphs, not ordinary graphs, not directed graphs. So a connected graph is kind of a generalization of the Euler trial, Euler-Tour theorem. A connected graph, G, okay, let's say it has 2k all the vertices. Okay, not two all the vertices. Have 2k, for example, 4 and so on, all the vertices. Then probably you cannot find 1k is greater than 1. Probably you cannot find the Euler trial to cover every edge, but you can find there are k trials, okay, whose union covers the whole edge set. And so this is something I want to prove. Okay, think a little bit about this. So if the graph G has only two odd vertices, you can find the one trial which cover all the edges. Now we have 2k, for example, 4. So let's say 4 all the vertices, and I ask you to give two trials whose union covers the whole edge set. Okay. What do you think? So you are don't forget to use the applied results we already know. So we can prove this all from the beginning, but also we can use the result, and also especially we can use that equivalence explanation I just gave you. So if you, okay, I'll just write down the proof. So say we have 4 v1, v2, v3, v4. Okay, in general we can write 2k vertices with all the degrees. I just want to remind you that technique we already used. So we add two edges. Let's say E1 is V1, V2, okay? And E2 is V3, V4, okay? And after adding these two edges, we obtain a new graph. G prime, which is an even graph. Right? Because all these 4 vertices right now have even degrees. So all vertices have even degrees because the remaining vertices, the degree do not change. The degrees do not change after this addition. And then apply Euler's theorem to obtain a Euler tour for G prime. Okay, so imagine we have a Euler tour. So I don't know how to draw this. So let's say V0, E1. So let's not draw anything. Maybe V0, E1, V1, E2. It's not very good because it's possible to have the same vertices. Okay, so V1, V2 could be the same vertices. It's just a way of writing. It's not very rigorous. So E3, V3, something like this, and somehow, and come back to V0. This is Euler. Suppose, so for example, is the Euler. Okay, so maybe it's better to write something like etc. Until here we have W, E1, W prime. Okay, and etc. We have say U is a vertex, E2. Here you have, okay, it's stupid because here I already have name V1, V2. So I don't want to E1, V2. Let's put W, W prime, and U, U prime. Okay. So here we have W, E1, W prime, and at some point we see U, E2, U prime, and we come back to V0. So this is a Euler. So imagine if what happens. So if we delete, because we want to come back to the original graph, if we delete E1 and E2, what do we have? So imagine if you have a cycle. This is not a cycle, but imagine you have a cycle. If you delete two edges, you get two paths, right? So the claim is that if you delete E1 and E2, we have exactly two files. Okay, one trial will be starting from, for example, W prime and end at U. Okay, the other trial starts from U prime and is come back to W. Okay, for example, this is my E1, and I see this vertex is W, and this vertex is W prime, and probably this is E2, and this vertex is U, and this vertex is U prime. Okay. So I delete these two edges, I got two trials. And these two trials, its union, their union covers all the edges. Okay, this is the proof. Okay, I like this because it's remind ourselves the beginning of the equivalence of the two theorems of Euler and Euler trials. You have this technique by adding edges and take it back when you need. Okay, are you happy? Right. So this is the plan. I have some other questions. I put in my notes one problem of IMO in the 90s, in the 1990. It's a little complicated, and it's a little. I don't think it's as important as these theorems. So you can read it if you have extra time. I'll put it in the Google Classroom. Okay. I think that's enough for today. I will put another list for you later today. Okay, so let me stop the recording.